All right, so we're continuing the discussion of condensers here. I'm on this page right here. There's a knowledge requirement there for why we would want to remove non-condensable gases. And so, like we said, we have a condenser. Generally, it's going to be a cross-flow heat exchanger, and I'll just put a simplified one up here. Here's the condenser, and down at the bottom, I'm going to put the hot well. And we said that we're going to have circ water flowing through tubes, and then it leaves. And then steam would be coming down, oops, wrong color, would be coming down across the tubes after it was discharged from the outlet of, say, the low-pressure turbine. And the entire time we know what's going on, we have a reduction in specific volume of the steam. So the steam, as it's condensing, specific volume, V sub x we'll say, is going down. And that tends to help us increase our vacuum. And remember, a good vacuum is necessary so that we can extract as much work out of the turbine as possible. Also, this down here, this hot well right here, will provide a couple uses. This is where we're going to take a suction with our condensate pump, and the condenser ends up doing a couple things. Air and non-condensable gases will escape or be liberated, and then we can use something to remove that, because there's a couple things that are bad if that's allowed. First of all, condenser pressure would go up. That's not a good thing. We know that work of the turbine would go down. And also you can get blanketing of the tubes with air. And so you get poor heat transfer if the air were to blanket these tubes. So what we can do is we can have a mechanical vacuum pump initially to start up. And this is called a mechanical vacuum pump, or sometimes called a hogger. Sometimes this thing is called a hogger, kind of a colloquial name for it. And this will eject, normally upon startup, to somewhere around 20 inches of mercury vacuum. I could get the condenser pressure down pretty low. And then, obviously, we would use steam jet air ejectors to remove the air and non-condensable gases during normal operations. Steam jet air ejectors. So, a couple things. Air non-condensables, they get liberated during this process of condensing the steam, and we remove that normally with steam jet air ejectors, or initially upon startup, we can use a mechanical vacuum pump. Some other things here, this hot well, it provides a stay time. So it should be sized such that there's enough time for, in our case, a boiling water reactor, such that nitrogen-16 decay gammas, the nitrogen-16 could decay away such that when the condensate pump takes a suction from it, rad levels are significantly reduced because these nitrogen-16 decay gammas have decayed away inside the hot well, and we're not going to be pumping it all throughout the turbine building now. This is vitally important that we have enough condensate depression here. Condensate depression. Now, condensate depression is nothing more than how subcooled is this water that collects in the hot well. And it's typically good to have about 8 to 10 degrees of subcooling, such that if I was operating, say, and you'll see this discussion here on hot wells and on how about air and non-condensables being not a good thing, you'll see that if you'll turn the page, we start talking about condensate depression here. Right? So if I assumed I had a 28 inches mercury vacuum in the condenser, and I was to look up the saturation temperature for that, I would see that it's about 102 degrees Fahrenheit. So this water, if it were saturated, would be at 102 degrees, and when I lower the pressure at the eye of the condensate pump, it would flash to steam, and we would have cavitation of our condensate pump. So what we're going to want to do is, as the steam is condensing, at some point in time, it has condensed all the way, and there's still some tubes left to actually subcool the steam so that it'll drop down as water. And we want that to be about 8 to 10 degrees below the saturation temperature. So in this case, I'd want it to be about 92, 94 degrees in the hot well if I was operating under this condition. Now, one of the things I don't want to do is to have too much subcooling. That's going to be horrible on our plant efficiency, because when we look later here, we'll see plant efficiency is going to look at the net work that we get out divided by the heat that we put in, heat added. And if we reject too much heat here, we're going to have to end up adding it back, driving efficiency of our plant down. So while some condensate depression is good, excessive condensation is horrible. It's bad on plant efficiency. It also, secondarily, it allows for increased air absorption in the water. So this air that was being liberated, it can get reabsorbed if the water gets too cold. So we don't want to do that. And that's discussed down here on the bottom. All right? So condensers and the operation of the condensers are pretty cool. In reality, up here in the neck is usually a series of baffles to make sure that we get good flow going across the tubes, the circ water flowing through in the tubes. And very often we're going to find out that there are feed water heaters located up here. So it makes it easy to actually get the extraction steam to the low pressure feed water heaters up here in the neck of the condenser. Right? So the next thing we're going to talk about is we're going to talk about a couple of our heat exchanger, our heat transfer equations. And this chapter here, it's not really supposed to be about heat transfer equations, but it's kind of leaked over into components. Instead of just talking about the components, we got to talk a little bit about the math. All right, so I'll see you in the next video.